Today we have a really interesting case study. It's the integral from 0 to infinity of e to the negative x squared times the cosine of a 3 by 3 matrix. So yeah, that is one hell of an integral. And the first thing to address here is, what does it even mean to take the cosine of a matrix? How is this thing defined? Well, it's defined in analogy to how we define the cosine function as an infinite series. That is, recall that the cosine of x can be expanded as its Taylor series, that is the sum over the non-negative integers n, of -1 to the n times x to the 2n divided by 2n factorial. So the cosine of a matrix A is defined as the sum over n of -1 to the n times a to the 2n divided by 2n factorial. So we're interested in the even powers of our matrix here that for reference purposes we're going to call A. So what does it mean to evaluate a to the 0? Well, that's defined as the identity matrix, and in this case the identity matrix of order 3. And what about a squared? Well, a squared just means a times a. So multiplying a with itself, this gives me 0xx 00x 000 times 0xx 00x 000. So carrying out the matrix multiplication gives me, for the first entry, I get a 0. For the second one, I get a 0 as well. And for the third, I get x squared. And for the rest of the matrix, I'm going to get 0, 0, 0, and again 0, 0, 0. So that is a squared. Now, what about a to the 4th power? Well, multiplying a squared with itself, it's easy to verify that this thing is the 0 matrix of order 3. So that means a to the 2n equals the 0 matrix for n greater than or equal to 2. Okay, cool. So that means we're only interested in 2 terms for the infinite series expansion here on the right-hand side. That's a to the 0 and a squared. So expanding the right-hand side for the given matrix gives me a to the 0, that's I sub 3 minus 1/2 of a squared. Okay, so we're pretty much good to go. And all that's left to do is just combine the results according to the equation we have for the cosine of the given matrix. And this means that the cosine of A equals 1, 0, -1/2 x squared, 0, 1, 0, 0, 0, 1. And this matrix was being multiplied by e to the negative x squared. So that just amounts to the scalar multiplication of a matrix. And that means we have to multiply all the entries by e to the negative x squared. So we have e to the negative x squared here. 0, -1/2 x squared times e to the negative x squared. And we have, again, these Gaussian terms along the diagonal and zeros everywhere else. Okay, and now to integrate this thing from 0 to infinity. Integrating a matrix function amounts to integrating the individual entries. So that means we have integral 0 to infinity e to the negative x squared dx, and exactly the same integrals all along the principal diagonal. We have zeros here, 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 and here, and there. And we have one more integral that's from 0 to infinity. -1/2 that integral, that is, and we have x squared times e to the negative x squared. Now for the principal diagonal, we have the beautiful Gaussian integral. So that means we have root pi by 2, root pi by 2, and root pi by 2, which looks wonderful indeed. Again, we have the zeros, and we still need to evaluate this integral here. And to do that, we need some help from our old buddy, the gamma function. So let's define I sub 1 as the integral from 0 to infinity of x squared times e to the negative x squared dx. And we're going to make the substitution that is x squared equal to u, which implies that x equals root u, and further implies that dx equals 1/2 times u to the negative 1/2 du. And the limits of integration are clearly not bothered, so I sub 1 in the u world is 1/2 the integral from 0 to infinity of u times e to the negative u times u to the negative 1/2 du. That means I have 1/2 times the integral from 0 to infinity of u to the 1/2 times e to the negative u du. And this thing here is the gamma function evaluated at 1/2 plus 1. So this implies that I sub 1 equals 1/2 times gamma 1/2 plus 1. And by the recurrence formula for the gamma function, we know that gamma z plus 1 equals z times gamma z. So in this case, we have z equal to 1/2. And we know that gamma 1/2 equals root pi. So that means we have a quarter of root pi, which is again quite nice. So that means our target integral I sorts out to factoring out all the root pi by 2 terms. I can write this as, why can't I write the letter I anymore? Much better. So we have root pi by 2 times the matrix 1, 0, and we had negative 1/2 times I sub 1. So that means we're left with negative 1/4, correct? Yeah, that's about right. And then we have 0, 1, 0, 0, 0, 1. And that concludes the solution development for the matrix integral I. Also, it concludes the holiday special that has been going on since December the 1st. And I had lots and lots of fun. And before I sign off, thank you. It's been an incredible year. It's been amazing. Last year, around September or October, I had, barely 200 subscribers, and I suddenly decided to start doing integral videos because I had decided that if I want to do YouTube, I'd rather do stuff that I really, really like, stuff I enjoy, stuff I love, and I love solving integrals. So I kept posting videos on integrals, differential equations, infinite series expansions, and the occasional physics video, and you tuned in, you watched my videos, you liked, subscribed, commented, criticized, provide feedback. I am thankful for every little bit of it. I am thankful to each and every one of you. I am thankful for each and every one of you. You are all incredible. I hope you enjoyed the video. Be sure to like and subscribe. I'll be back after January the 1st. I think I'll start uploading content again by January the 2nd. And for the next few days, I'm just going to be moving the complex analysis lectures to this channel so that when the new year starts, I can add more videos to that playlist as well so that we can complete the complex analysis course that I had started. Thank you. See you next time.